Hello, and welcome to this presentation, Understanding Transformer Testing. In this presentation, we'll provide a short technical overview of the most common transformer measurements and how these measurements are made. Transformers are most often tested and measured using LCR meters. If you're unfamiliar with LCR meters, or if you'd like a brief refresher, you may want to watch the presentation Understanding LCR Meters before beginning this presentation. Let's start by briefly discussing what we mean by transformers. Transformers are devices that are primarily used to convert AC voltage levels. For example, a step-up transformer increases the voltage, and a step-down transformer decreases the voltage. In addition to converting voltages, transformers can be used in other applications, such as impedance matching. Another common application of transformers is isolation, which is often used for safety reasons. This presentation covers measurements made on the transformers used in electronics applications. These transformers are typically small, work on relatively low voltage or power levels, and are used for indoor applications. We won't be covering the larger outdoor transformers that are used for electrical power distribution, although many of the tests described here also apply to these larger, higher power transformers as well. Transformer operation is based on something called mutual inductance. That is, the coupling of a magnetic field, or flux, between two inductors. We'll cover this in more detail later in the presentation. Inductors are made by winding wire into coils, usually around some kind of ferromagnetic core. In transformers, these coils are called windings. Generally speaking, the higher voltage side of a transformer is called the primary, and the lower voltage side is called the secondary. And finally, note that there are many different ways to construct transformers. The biggest variables are often things such as the core material used, the orientation and number of windings, etc. Since mutual inductance is the basis of transformer operation, LCR meters are the most common instrument used when testing transformers. In addition to their ability to measure inductance, LCR meters are a good choice because they can measure capacitance, resistance, phase angle, etc. Some LCR meters also have special transformer measurement functions. Note that a special test fixture is sometimes required when making certain types of transformer measurements. And like most other types of measurements, measurement accuracy can be improved using compensation or calibration routines to reduce or remove the effects of fixtures and leads. The 5 most common types of transformer measurements are turns ratio, mutual inductance, phase angle between primary and secondary inductance and secondary inductance, and leakage inductance. The first 3 of these are measured by connecting an LCR meter to both windings, and the last 2 are measured by connecting to only one winding. In the remainder of this presentation, we'll explain what each of these measurements are and how they're made. Turns ratio is perhaps the most fundamental measurement of a transformer. This is because voltage transformation is proportional to the ratio of turns on the primary to turns on the secondary. For example, a transformer which has 10 times more turns on the primary than on the secondary has a turns ratio of 10, and this would step 120 volts on the primary down to 12 volts on the secondary. Therefore, one simple way to measure turns ratio is to apply a known voltage to the primary, measure the voltage on the secondary, and then take the ratio of these two measurements. Later in this presentation, we'll also discuss another way of measuring the turns ratio of a transformer. As stated earlier, mutual inductance is the basis of transformer operation and refers to the fact that current flowing in one winding creates a magnetic field or flux that induces a voltage in the other winding. The mutual inductance of a transformer is a function of the construction and the orientation of the windings. For example, parallel windings have higher mutual inductance than perpendicular windings. Another example is that the mutual inductance increases with increasing core permeability. We can measure the mutual inductance of a transformer by simultaneously connecting to both the primary and secondary and measuring voltage and currents on each side. The math used to derive mutual inductance, M, from these measured values is somewhat complicated, but the end result is a value in units of henries. In transformers, a high mutual inductance is usually desirable because it represents more efficient coupling of flux between the two windings. Phase angle refers to the fact that transformers have polarity, in the sense that the input and output voltage will have the same sign at the same time on leads that have the same polarity. In some cases, transformers will have markings in the form of dots, etc., to show which leads have the same polarity. In an ideal case, there would be zero phase shift between signals with the same polarity, but in real transformers, there's usually a non-zero shift or angle between the signals on each winding. In addition, this phase angle tends to vary with frequency, often substantially. Measuring the shift or phase angle is relatively straightforward. We simply connect to both the primary and secondary windings and measure the phase difference between the two voltages. Note that if you get a phase angle of roughly 180 degrees, this is often an indication of a polarity mismatch between primary and secondary. In this case, it would be a good idea to check that you haven't reversed one of your connections to the transformer. Another very simple transformer measurement is determining the individual inductance of the primary and secondary windings. The inductance of each winding can easily be measured separately. For the primary inductance, we connect to the primary and measure with a secondary open. And for secondary inductance, we measure at the secondary with a primary open. It should be noted that measurements of primary or secondary inductance will also, unavoidably, include something called leakage inductance, an important topic which we'll cover in detail later in this presentation. One of the reasons why we might be interested in measuring primary and secondary inductances is that this is another way of calculating turns ratio. We simply take the square root of primary over secondary inductance. So how does this differ from measuring turns ratio using voltages? First, the voltage method gives the actual voltage transformation during operation, since we're directly measuring the primary and secondary voltages. Any losses, such as core losses and resistive or capacitive losses, are incorporated into this measurement, and because of these losses, the turns ratio calculated from the voltage method is usually greater than the physical turns ratio. The primary advantage of calculating turns ratio using inductances is that it usually provides a more accurate measurement of the actual physical turns ratio. Next, we'll cover leakage inductance. Let's start by looking at an ideal transformer. In an ideal transformer, all of the magnetic flux created by the current in the primary winding is coupled to the secondary winding. In this case, the transformer is essentially lossless, with no wasted energy or flux that does not get coupled to the secondary. The voltage in the secondary would therefore be entirely a function of the primary voltage and the number of turns in each winding. In real-world transformers, however, some of the magnetic flux doesn't get coupled between the primary and secondary windings. This non-coupled inductance is sometimes represented as an additional inductor in series, but keep in mind this is not an actual physical component. This additional inductance is called the leakage inductance because it represents that part of the flux that leaks out of the transformer and is not coupled between the windings. Leakage inductance is an important consideration in many applications, such as the design of power supplies, lighting ballasts, audio transformers, etc. In many cases, the goal is to minimize leakage inductance through careful construction of cores and windings, but there are some cases where it's useful to have a leakage inductance with a certain range of known values. We mentioned earlier that when we measure the primary inductance, this also includes the leakage inductance. Remember that this leakage inductance is not a separate physical inductor that we could connect to and measure separately. So how do we measure this leakage inductance? If we short the secondary winding, this will cause zero voltage drop across the secondary. Due to the nature of transformers, 0 volts across the secondary also causes 0 volts across the primary. This means that we can measure leakage inductance by shorting the secondary and then measuring inductance on the primary. Since shorting the secondary winding causes both LP and LS to be 0, the inductance measured on the primary is now only the leakage inductance. Let's end with a brief summary. Transformer operation is based on the coupling of magnetic flux between two windings or coils, whereby a current in one winding induces a voltage in the other winding. Transformers are primarily used in transforming voltages, but are also used for things such as impedance matching and isolation. Because they're designed to make precise impedance measurements, LCR meters are the most common instrument used to measure the transformers found in electronics applications. In this presentation, we introduced the 5 most important transformer measurements, namely turns ratio, mutual inductance, phase angle, primary and secondary inductance, and leakage inductance. This concludes our presentation, Understanding Transformer Testing. If you'd like to learn more about transformer testing or LCR meters, please see the links in the video description. Thanks for watching.